Intermolecular forces, or IMFs, are really important for being able to predict certain things about materials. And so I want to talk in this video about how we determine what intermolecular forces are present within molecules, and also talk about the impacts of those on the properties of that material. So let's take carbon dioxide, for example. If I do the Lewis dot structure for carbon dioxide, I'll see that I have two lone pairs on each of my oxygens and a double bond connecting my carbons and my oxygens. I know this has linear geometry, so it has a 180-degree angle here. Just a straight line. Two electron pairs around a central atom gives me that linear geometry. And when I look at the difference in electronegativities between carbon and oxygen, I can see that there are dipoles on each of the bonds. But because of the geometry, and when I add these two together, right, I add this one and then head to tail this one, then they just kind of cancel each other out. So even though the bonds are polar in this molecule, the overall molecule is nonpolar. So with carbon dioxide, if I'm trying to figure out what things cause carbon dioxide to interact with itself, right? How do carbon dioxide molecules stick to each other? Then because it's nonpolar, I can sort of visualize, and I'm going to re-sketch this here. I can visualize this linear molecule as having kind of an even distribution sort of throughout of my electrons. So when I picture the electron cloud, because it's nonpolar, it's a fairly even distribution of those electrons. So there's no one place that has more electrons than others. Although at any given time, those electrons can be clustered up on one side or the other, and that causes there to be an induced dipole where there isn't normally. So the only thing that's present for nonpolar molecules are what are called dispersion forces, or London dispersion forces, or van der Waals forces. So that's the only thing that's present. I can't have a dipole-dipole, I can't have hydrogen bonding. None of those things can be present because I don't have a polar molecule. So the only thing there are these dispersion forces. So I would say, just based on that information, that because this is the weakest of the intermolecular forces, there's probably not a lot of attraction between those carbon dioxide molecules. There's only this kind of weak induced dipole that happens because of the random distribution of electrons. So these things aren't going to interact or stick together with any sort of strength. Okay, let's compare this to ammonia. If I do the Lewis dot structure for ammonia, and I have a lone pair and three hydrogens that are bonded there. When I think about the geometry of this thing, that I have four things around a central atom, so I'm going to draw it like a tetrahedron because it's got tetrahedral geometry. And then I can see that because three of those electron pairs are atoms and one of them is a lone pair, that I have this trigonal pyramid geometry. So it's just kind of the base of the pyramid there, like that. Kind of looks like this guy. So there's my base of my pyramid. That is this molecule. Now if I look at the hydrogen to nitrogen bond, just kind of out of context, nitrogen is more electronegative than hydrogen. So if I look at my electronegativity table, the difference between them is greater than that 0.4, which is kind of our cutoff to find the polarity of a bond. So if I have all of these dipoles, each one coming up the bond here from each of my legs. So I have one that's pointing up this way, one that's pointing up this way, one that's pointing up this way. When I add them all together, head to tail, I'll end up with a net dipole right up through the center of this molecule. Okay, which means that I have one side that is slightly negative and one side that is slightly positive. So that base of the pyramid there, where the hydrogens are slightly positive. The nitrogens kind of sitting there at the top with the lone pair on it is going to be slightly negative. So that net dipole means that I have a polar molecule. That automatically means that when ammonia interacts with itself, because it's polar, we're going to have dipole-dipole attraction. Oops. Pardon my line there. Dipole-dipole. Because dispersion forces are in everything, it also has dispersion forces. Because of the random motion of electrons, then there will still be dispersion in this as well. It's not going to be as much of an impact because it's so much weaker than the dipole-dipole. And now we need to figure out, well, if I have multiple of these guys hanging out, what other factors do I have? If I have another one of these guys, let's have this one down here hanging out with its little lone pair, the slight negative, slight positive. So if these are interacting together, this is the dipole-dipole attraction, but it is also hydrogen bonding because I have a slightly positive hydrogen on one molecule and a slightly negative nitrogen on the other. So we also have hydrogen bonding in ammonia, which is the strongest of the intermolecular forces. So dipole-dipole, hydrogen bonding, which really kind of covers dipole-dipole, but we could say that all three of them exist. That tells me that there's really strong attraction with ammonia. So ammonia is really attracted to itself. Okay, so that gives me information about how the characteristics of ammonia are going to be, how it's going to react with other things. So that's how we determine the intermolecular forces, is it's based on the polarity of the molecules themselves. So you have to do the Lewis dot structure, you have to figure out their geometry, you have to find the net dipole, and then that will give you information about how they are going to interact with other things. Now, how strong those attractions are, the more forces, the more IMFs there are, then the stronger some of the properties of those materials are going to be. I'm focusing really on liquids here and the interaction between liquids and gases, because that's really where these intermolecular forces come into play the most. It impacts things like viscosity. Viscosity is how resistant a liquid is to flowing. So if you're thinking about examples of this, you can think about things like maple syrup or honey or molasses, something that has kind of a thickness to it. And viscosity and thickness are kind of different because we usually think of thickness and density as being the same thing, how tightly packed the particles are. But viscosity is really how much is this thing flowing or not flowing. And so that resistance to flow is viscosity, and the better it sticks to each other, so the stronger the intermolecular forces in the liquid, then the more viscous it's going to be. Because it likes to stick together, because it wants to stay together, so it's not going to flow as easily through a pipe, or it's not going to flow as easily through a line in your engine or whatever's moving around. You could talk about viscosity of like oil, for example. Another characteristic that is impacted by the intermolecular forces and their strength is boiling point. So boiling point is the temperature at which the atmospheric pressure is equal to the vapor pressure. And recall that vapor pressure is the pressure of the gas, the partial pressure of a gas over the surface of a liquid. And so when that vapor pressure is equal to the atmospheric pressure, then the liquid begins to boil. And so if we have a strong attraction between the liquid particles, the stronger the attraction, the harder it is to get it to boil. So the stronger my IMFs, the greater the temperature that is needed to cause boiling to happen. So I have to put more energy in order to get it to go from the liquid phase to the gas phase. Because if we're kind of picturing our surface of our liquid here, and there's particles that are coming off and there's particles that are kind of coming back in. So here's my liquid phase. Then the stronger these guys are attracted to themselves, the less they want to be off in the gas phase. And the less gas there is, the less vapor pressure there is. So that's going to have an impact there as well. So the greater the vapor pressure, the greater the boiling point as well. Because we have more gas exerting pressure onto the surface of that liquid, that's going to make it harder for the liquid to boil. Okay, now if we think about this in terms of proximity, if I go up to the top of a mountain, so here's my mountain, that's pretty good, then you increase in altitude, then that decreases the pressure, the atmospheric pressure, because you have less atmosphere over you. So you go to the top of the mountain, you have less altitude, less atmospheric pressure. If you have less atmospheric pressure, then it's going to take less vapor pressure to get you to a boiling point, which means that the boiling point decreases as your altitude increases. So for example, at sea level, water boils at 100 degrees Celsius. We know that. That's the boiling point of water. But if you go to Snoqualmie Pass, which is a pass between where I live in Ellensburg, Washington, and Seattle, Washington, there's a mountain range, and at the elevation of Snoqualmie Pass, water would boil at 96.3 degrees Celsius. So that increase in altitude is going to decrease the amount of atmospheric pressure, which increases the vapor pressure, which is going to increase, or it's going to, sorry, it's going to decrease the atmospheric pressure, which means that less vapor pressure is required, which means the boiling point is going to go down. There we go. It's kind of hard to get your head around. All right, another characteristic that is impacted by IMFs is surface tension. So that's that skin at a surface of a liquid. We know that a water droplet, if I have a piece of kind of waxed paper or something, we've all seen water bead up like this. There's this kind of pulling in of the water. It's more attracted to itself, and then it creates this kind of skin on the outside, right? That surface of the water droplet. We see that as water is falling from the sky, right? We have kind of a raindrop sort of looking because of the gravitational pull on the mass. So as it's pulling down, it creates this kind of raindrop sort of look. And the skin around the outside is because the water is all pulling inward because of its attraction to itself, because water has dipole-dipole, hydrogen bonding, and dispersion forces that causes it to create this skin. You might have also experienced this if you've ever done a belly flop in a pool, right? The surface tension of that pool, and you try to break that surface tension with your surface area of your body, then that causes a lot of pain and suffering because of how strong that bond is between the water molecules. Okay, now let's talk a little bit about capillary effect, which is also something that is impacted by intermolecular forces. These intermolecular forces can be kind of combined together in the way that they interact with themselves and the way we interact with other things. So we have kind of internal stickiness. So how sticky are these molecules to themselves? We talked about that with the carbon dioxide and the ammonia. The technical term for that is cohesion, right? If something is cohesive, it means that it's all internally kind of consistent. So if we're thinking about this in terms of science, then this cohesion is the stickiness of molecules to themselves. So that means that the greater the intermolecular forces, the greater the cohesion. Adhesion is stickiness to other things. Think like adhesives, like glue or tape. So that would be stickiness to other surfaces. If we take a straw, let's take a small kind of glass capillary tube, which is like a tiny skinny straw. This is used in like blood donation and other medical kind of applications. So if I have a water droplet here and I stick my little capillary tube in, then the water, without me providing any force or suction or anything like that, the water is going to automatically rise up the tube. And why it does that is capillary effect. If I was to kind of make this tube a little bit wider so that I could see what's going on, my water molecules are going to be attracted to, because of their intermolecular forces, they're going to be attracted to the sides of the tube. And they're going to kind of climb their way up. And then the water molecules are also going to be attracted to each other. So there's this kind of combination of adhesion to the sides of the wall and cohesion to each other. So that causes the water level to rise. This is also what causes the meniscus, that curvature of the liquid inside the tube. And you've seen that if you've seen a straw, for example, you can see that over the surface of a liquid. So the combination of adhesion and cohesion from these intermolecular forces causes that liquid to defy gravity. Kind of a cool feature.